there's going to be two main ways that we see bonds being broken. The first is called a heterolytic bond cleavage. So in heterolytic bond cleavage, we see a bond between two atoms like A and B. And of course, that line means there's two electrons there. And what happens here is we take a set of those electrons and then they live on either A or either B. So basically, in this, we're going to have ions forming. So the result of that step here, right, if we were to do that, is that you have A, that would have a formal plus charge, and then B would have grabbed those two lone pairs, and we would have an electron charge here. An example of this might look something like this. So in organic chemistry, we might see something like this here. All right, and that chloride might take that set of electrons away with it. So that flow of electrons is what we would use, that arrow. And that would give us a CH3, carbon, carbon, carbon with a plus charge. And then, of course, chloride would be produced also. So that's heterolytic. Homolytic is the type of bond cleavage that we see when free radicals form. So for homolytic, we're really looking at radicals. So for A and B, if we have A connected to B, if you remember, for a radical, we use this little fishhook arrow, right? So we'd see one of those electrons coming over to atom B and one electron coming over to atom A. That would give us an A radical plus a B radical. And that's what we're going to be looking at in this chapter. So an example of that would be chlorine. So chlorine has all those lone pair on it, and this bond can be homolytically cleaved. And that would form here, in this case, two atoms that are the same. So I'm going to write a 2 here. And then we'll put, I'm just going to highlight that radical as being a little bit bigger, that electron, just to make sure you see that there. But that would be an example of your homolytic bond cleavage. Now, we can look at homolytic bond dissociation enthalpies. We're going to call those BDEs. And we're going to look at BDEs throughout the year, really to make comments about stability of intermediates. So it'll be something that comes up that we need to remember. Now, recall from our last little section here that, that homolytic means radicals form. Okay, so when we talk about these numbers, and we're going to see them as we go throughout this chapter, we need to look at them in a little bit more detail. So if we look at this reaction, this is an observed reaction right now, okay? So here's an observed reaction. This is a free radical reaction. And we're starting off here with methane. So here's our methane. We're adding to that chlorine, and we're getting an alkyl halide and hydrochloric acid. Now, we can look these numbers up, so you never spend time memorizing them. In fact, the numbers are always being updated to more accuracy and stuff. So you'd look these up. But when you look up the CaH3H BDE, you get 104, right? 58 for chlorine, 85 for this bond, and 103 for H and Cl. Now, that's the amount of energy required to break the bonds, and this is the amount of energy released when those bonds form. Right? So what we're going to be looking at here is this. Our delta H is going to be equal to the BDE of bonds that are broken minus bonds that are formed. Okay, so it's broken minus formed. Now the broken is on our reactant side. Formed is on our product side. So in GChem, you probably did products minus reactants. Here we're doing reactants minus products. And that's because these numbers are reported as being positive. So when we go through, we get 104 and 58. Right, that's here. 104 and 58. That's broken, sorry. That's what we broke. And then formed over on this side, 85 and 103. Right here. And when we put all of that together, we get negative 26. So that's the delta H for the overall observed reaction. Now, we can use these BDE values to predict stabilities. That's one of the things that we're going to be looking at in this chapter, is the stability of different type of radicals. So let's look at a process. Here we have an R, and do you remember an R just means carbon atoms? Okay. Now that carbon can be different things. So we're going to look down here. What if it's connected to just one carbon here? Right. What if that carbon is connected to another carbon? Remember that's what we would call a primary. Right here we're connected to 1, 2, so that's secondary, and then here we're connected to 1, 2, 3. That gives us tertiary. So we're going to look at methyl, primary, secondary, and tertiary. And the step will be the same. Right? So here we're losing our electron. Right? So that's your homolytic bond breaking there, bond cleavage. And H nu, we haven't really gotten into this yet, but this means light. So it's your delta E equals H nu. It's a photon of light. So we'll talk about how that's involved in a little bit when we look at the mechanism. It's not actually involved in this particular step, but for the observed reaction to occur, we need to have that there. All right, so let's take a look at the trend. So the methyl's 104, right? Coming down to primary are 98, secondary is 95, tertiary is 91. So this is an increase in our potential energy as we go up, and actually as we go over to this side, we're becoming more stable. So a lower BDE means that you have a more stable intermediate. So it's interesting. There's a question here. Why is this occurring? Why are these tertiary radicals more stable than primary? They're all just carbon-hydrogen bonds that are breaking, right? It's that bond that breaks in every one of them. So that doesn't have anything to do with it. It must have something to do with the nature of that carbon and that tertiary position. Right? So what's happening around here where we get that plus charge must make a difference. And that's what we're going to look at in our next section, a topic called hyperconjugation and electron donating groups.